Hey guys, we're going to go ahead and do the scientific method, which is the first part of module 1. I know the lighting in here isn't super great right now, but I figure you're not here to see me anyway, you're here to see the notes. So let me share the screen here. Give me just a second to get some of this set up on my end. Okay. So let's go ahead and go over this pre-lecture assignment. Again, ideally, you will have finished this assignment before you're watching this lecture, okay? And you should have read pages 9 through 12, the e-text, so that you can fill out this information. All right, so science is the way of knowing about the natural world. Scientific method is a systematic process to arrive at truth. Steps: observation, hypothesis, experiment, result, confirm a hypothesis or not. This is also evaluating your data. And then conclusion. Okay, so when you are making an observation, we want to have our observations be something that you can both see and watch and measure it. Okay, so these are called objective observations. Objective because somebody else could look at the same thing that you're looking at and also see those same things and be able to take those same measurements. The opposite of this is called subjective. So subjective observations are really based off of personal opinion and preference. So something that's subjective would be to ask people if they prefer Sierra Mist or Sprite. Okay, that's going to be subjective, just depending on their preference. If you wanted to make that objective, then you would collect data after asking multiple people and then take an average, and you'd be able to present some numbers that show, well, most people seem to prefer this. The numbers show that most people prefer this drink over this. Okay, so the next step in developing a hypothesis. So first off, a hypothesis is a possible answer or explanation for a natural event and is based on existing knowledge. It's also based off of the observation. Okay, so you see something, you have a question about it, you develop a hypothesis for why that thing is. Okay, a hypothesis must be both testable and falsifiable. Okay, in other words, you need to set it up so that you can prove it wrong. I know that that seems backwards, but in truth, when it comes to scientific experimentation, you're trying to set up your experiment to see if you can prove it wrong rather than setting it up so that you're sure to get it right. It's kind of like eliminating all of the possibilities, and if you eliminate the possibilities, then whatever is left is most likely true. That's how hypotheses are tested through experimentation. An experiment is a series of procedures to test a hypothesis. Okay. A good experimental design includes an experimental variable. So this is the thing that's being changed in the experiment. It's what we're testing for. It also includes a treatment or a test group, and this is the group that's exposed to the experimental variable. And then it includes a control group. A control group is not exposed to the experimental variable. So if you're testing medication, the new medication versus an old medication, new medication is the variable, right? The medication is a variable. The treatment group gets the new medication. The control group gets the existing medication, and then you can compare the results that way. Finally, you're going to collect and analyze or evaluate your data. Data is an awesome character on Star Trek: The Next Generation, but they are also the results of your experiment, and they're often presented as tables or graphs to make them more visually understandable quickly. Okay. I remind you here that you should have also completed the quiz for this chapter, the Connect quiz, and usually do that after you do the reading part. Okay. All right, so this next part here, this is where kind of what I was talking about when it comes to the experimentation, talking about, how you can test if one antibiotic is better compared to another. So basically, we're going to go with something like blood pressure. Okay. We're going to say that we're testing blood pressure medication. Oops. Okay. And so we have our new medication. It's A. And existing meds is B. We're here to see if we can design an experiment that will let us test to see if our hypothesis that A is better than B, see if there's a way to test if that is true or not. Okay. So obviously you're not in a classroom to do this in groups or with partners, but take a second and kind of think through it. What would you need in order to set up an experiment that you could prove wrong, but that would also give you the data that you require to know if this medication is superior? All right, so we know first off that we're going to have, I'll identify it here actually, our variable, which in this case is the medication, right? The test group is going to get the new medication, and the control group is going to get the existing medication. Why don't we not give any medication to the control group? Why don't we just let them have nothing and see what happens? That's a medical ethics thing, because as you can imagine, we're not testing blood pressure medication on people that don't have an issue. We're testing it on people that require medication. So you can't just not treat your control group, right? You can't not treat their existing condition. So we have to keep them on medication. The way that we do that then is by putting them on medication that has existed for a longer time. You already have information on the data on side effects, the percentage of the people it works for. So we're going to use the existing medication to compare the results we get from this new medication. Okay. All right. We have, so when it comes to what kind of factors need to go into selecting our groups, we need to start thinking about things that could potentially cause issues if they're not uniform across all groups. For instance, you probably want to have an age range that your group falls in. You probably don't want to do something with, individuals between 20 and 65. Probably want to look at something more like 40 to 65. And you keep that consistent for both your test group and your control group. You'd want to know what their pre-existing conditions are. So in other words, maybe you want them on, you want to have your groups consist of individuals who are on medication for the same underlying condition so that you don't get a whole bunch of other conditions, each of which could be affecting the success of the medication that's being given. You might want to narrow this down by ethnicity, since certain ethnic groups have been shown to have different rates of disease depending on the disease. So you might want to have specific ethnicity, and you might want to narrow it down to a specific sex, like men only. Whenever I use this term in class, unless I'm talking about reproduction, I am talking about somebody's genetic makeup. So I am talking about whether the person is, XX female or XY male, okay? Or XXXY or XXX. That's what I'm going to be referring to. So when I'm using that, I'm not using it kind of like it's used in social science. It is specifically talking about the genetic makeup that identifies sex biologically. Anywho, just so that you know that now. So these are some of the things that you'd want to think about as far as setting up an experiment, because if you have, let's say that you have men and women, and some of them have congestive heart failure, some of them have kidney disease, some of them have arterial blockages, and you put all of that together and then try to use this medication on it, you're like, well, I can't really tell if the medication worked because the person had this particular condition, if it didn't work because they had that condition. You want to make it as focused as possible, okay? You also need to have a large sample size, and this is true for any experiment. You can't go out with 10 people and really determine much of anything. Even if we go back to that Sierra Mist versus Sprite example, 10 people isn't going to be enough. In a lot of cases, 100 isn't enough. You've got to have a few hundred to thousands, depending on the type of experiment and type of study, so that when you come back with a percentage, it's a more accurate representation of the broader population, not just a tiny subgroup. Okay. All right. So let's look down here at our graphs. Data, again, results of experiments. Line graphs are best used for continuous measurement over time. Okay, so you can kind of see as time passes what the different points on the chart are. So it's kind of a clear and efficient way to be able to convey this type of information. Bar graphs are great at showing one-time measurements. We'll pretend like that's going to fit. So in this case, it's showing the percent of people treated and the percent of ulcers cured. And this is a one-time measurement. It's looking at each group on the whole, rather than looking at the percent of ulcers cured over time. Standard error, which is represented by these bars right here, they look like T's. And here they look like an I that goes straight through, like the letter I. That shows the variation between subjects. So you're always going to have your outliers, the ones that are way high above average and the ones that are way low above average, or way low below average. Wow, I can't believe I couldn't get that out quite right. Anywho, and then you have kind of the number that's being charted, which tends to be average. Okay. All right, let's go here. I'm going to ask you to pause for a second, just pause the lecture and read through this and write down your own answers real quick, or come up with your own answers. It should just take a minute or two. I do suggest you do that because it helps to reinforce your graph and data reading skills. So pause it here, then we'll go over it. And here I am assuming you've paused it. Let's go over it. All right, so from this graph, can it be assumed that gum recession continuously increases over time? Well, we've got one of these graphs here, so we know that we are looking at something that's continued measurement over time. We have years after initial onset. Years would be a measurement of time. Over here, we have gum recession occurring in millimeters. So we will look at year 1, we're at about 3.5. I'm going to jump over here to year 4. We've come all the way up to 5. And by year 6, we're at 7. So can it be assumed that gum recession continuously increases over time? Yes, it can. We can see it displayed very nicely right there. Okay, periodontists, I can do this. I'm having a hard time tonight. Periodontitis, thank you, is categorized as moderate when gum recession is measured at 5 millimeters to 7 millimeters. So that's the moderate range. On average, how many years after onset does a patient fit into this category? All right, this is our bar graph here. So we're looking at a one-time measurement. This is still gum recession in millimeters, but here we're looking at the brushing pressure. So oh, I'm jumping ahead of myself too. I apologize, guys. This is going to happen sometimes. I have like long, crazy days, and then I will try to do the recording at night when the kids are in bed. But by then, my brain is fried. Let's try this again. On average, how many years after onset does a patient fit into the 5 to 7 millimeter category? All right, so here's our 5. Here's our 7. We start running into this right here, and obviously right here. So really between years 4 to 6. Okay, now let's look at toothbrushing pressure and gum recession. From this graph, can it be assumed that brushing pressure has no effect on gum recession? Well, let's look. Light brushing pressure, we get about 2 millimeters. Moderate, we get about 3.5. And heavy, we get about just over 6. So it seems to show that brushing pressure absolutely has an impact on gum recession. So this is wrong. No, we can't assume that it does not have an effect because it appears to. Based on the data in this chart, what advice would you give a patient who is showing early signs of gum recession? So this is one of those things that you're going to get in science a lot. Hey, here's this information. Now you need to decide how to use it, how to apply it. So here's the information. We know that brushing pressure does have an effect on gum recession. A patient is showing early signs of gum recession. Given what you know, what would you tell them? Well, you'd probably tell them, don't brush so hard, right? Use less pressure when brushing. A lesson for us all. Okay, moving along. Okay, so scientists use different reasoning tactics when forming hypotheses and conclusions. So just like there are objective and subjective observations, we have inductive versus deductive reasoning. Both approach a set of information in a different way, and I'm sure you'll find that one is a more logical choice for scientific reasoning. So let's start with deductive reasoning here. Deductive reasoning takes general observations and applies them to create specific conclusions. We'll do an example of this in just a minute. Okay, also in deductive reasoning, generally goes that what is true for the group is true for the individual. So what's happening here is we're going from a big side, right? General observations, lots of big observations to a specific conclusion. We're going from what's true for a big group is likely true for the individual, from big to small, okay? Frankly, the conclusions that are arrived at via deductive reasoning are generally correct because you have a lot of evidence to support the reasoning for your hypothesis. All right, so an example of this is this sweet young man here. His name is Adam. The instructor that created this portion of the lecture, this is her son, and her son has, he's autistic. Okay, so she uses him and his situation as an example of what happens with deductive versus inductive reasoning. So for, again, example, Adam, which is the instructor's son, this is him. We take into account Adam. What we look at first is the general knowledge that all autistic kids have 3 characteristics. Okay, and those 3 characteristics, by the way, are difficulty in socializing, repetitive behaviors, and narrow interests. Okay, so all autistic kids have these 3 characteristics. Adam has these characteristics. Therefore, Adam is autistic. Okay, that's an example of how deductive reasoning works. You take what is true for the group, for a large number of people, and apply it to a specific situation to come to a specific conclusion. Inductive reasoning is pretty much the opposite. It goes the opposite direction. You've got specific observations. You take those specific observations to create a general conclusion. In other words, what's true for one is true for all. As you can imagine, conclusions that are reached via inductive reasoning often incorrect. In the case of Adam, it would be like saying Adam, her son, likes to be touched and hugged. With inductive reasoning, we'd say, well, Adam's autistic. He likes to be touched and hugged, so all autistic kids like to be touched and hugged. We know that that is not true, and that also is something that is commonly found in autistic individuals. Don't always like to be touched and hugged. So this would be like Adam likes to be touched and hugged. Therefore, All autistic kids like it. Okay. You can also do this on a more ridiculous level, which being ridiculous, it helps to kind of drive the point across. That'd be like seeing me and being like, she's a redhead and she teaches science. All redheads must teach science. Okay. Nobody would come to that conclusion, at least, I guess not if you're from this earth. Maybe an alien would, I don't know. But you know that would be a really crazy assumption to make. That would be a result of inductive reasoning. Okay. All right. Again, you can't work in groups of two. I guess you can call on your roommate and be like, hey, you want to do this? Call your significant other. Date night. Who doesn't want to have a date night trying to figure out if these scenarios are using inductive or deductive reasoning? Right? Come on. Okay. If you're not working with anyone, let's go over these. We have to decide if these are examples of inductive or deductive reasoning. The steroid dexamethasone was tested in a small clinical trial and found to be effective in reducing death rates in severe COVID-19 patients. This drug will be an effective way to treat worldwide cases of severe COVID-19. So let's take a look at some clue words here to help us decide. First off, small. This was a small clinical trial, and the small results, or the results of this small trial, could be used worldwide. Okay, right there, we know we're going from something specific to something general, something small to something big. This is clearly a case of inductive reasoning. Okay. All right, in general, patients with pink eye, also known as conjunctivitis, exhibit eye redness, itching, discharge, and crusting around the eyes. This is such a great question. Sam has these symptoms, so he must have pink eye. All right, first off, stay away from Sam. If you've had contact with him, wash your hands and don't touch your face. All right, let's look at some of our clue words here. First off, we have in general. Okay, generalization, not something super specific. In general, we have all of these things. Sam, which is an individual, Sam has these things. Therefore, Sam must have pink eye. Okay, since we're going from big to small, from a group to an individual, we are looking at deductive reasoning. Okay, next. While making pasta, you notice that adding salt to the water makes it take longer to boil. You decide that salt, in general, must raise the boiling point of water. Okay, let's take a look at this. While making pasta, you notice that adding salt to the water makes it take longer to boil. Notice here that it doesn't say while making pasta over the past 25 years or while making pasta, with repeat experimentation. It just says basically you're making pasta. You notice that if you add salt, this thing happens. You decide then that in general, meaning in other words, kind of in all scenarios, adding salt raises the boiling point of water. Okay, so what's happening here, we're going from something specific, something you and you only observe, to something general that you figure must then apply to everything. So this is clearly another case of inductive reasoning. Okay, if you have a hypothesis that you reach based off of inductive methods, you can easily turn that into an experiment that would lead to a conclusion that could be obtained through deductive reasoning. In other words, you notice this one thing, let's test it on a much bigger scale and then see what we come up with. Okay. Oh, okay. Last page here. let's talk about a definition for a theory. All right, a theory is, here we go, a well-defined and accepted explanation that has been confirmed through repeated experiments. Okay, so if you think about some theories, including the Big Bang theory, how the universe essentially was created, evolution, those things are theories. They're very well defined, meaning they have specific steps that go along with it that make logical sense. And then repeated experiments have been unable to prove it wrong. Remember again that in scientific experimentation, the whole point is to try to prove yourself wrong, to prove your hypothesis wrong. If you can't prove your hypothesis wrong, and neither can anybody else as they test it, that hypothesis becomes a theory, okay? And then the more it gets tested over time, still not able to prove it wrong, that theory becomes more and more accepted as a very realistic possibility as far as the answer, okay? So like with both evolution and the Big Bang, clearly no one was standing here to watch that entire process, those entire processes happen. But the theories have held up because of repeated experiments. With Big Bang, it's using math, and a lot of the elements that are present on the Earth today kind of set up similar chambers to try to replicate the scenario. Evolution, a lot of it is in the fossil record, some genetic evidence. Anyway, those things have not been able to disprove the theories, so the theories remain. Okay. All right, so let's hit this question of the day. How do you science? And again, this was the example where antibiotic A is more effective than antibiotic B. I'm not going to go over it again because one, we just talked about it, and two, if you'd like to review it, rewind a couple minutes. Does anybody use Rewind anymore? Rewind is like a thing you did when you had a VHS or a cassette tape. Anyway, go backwards a little bit and you can review how we set this up. Okay, so this is kind of an example of how the text set it up. The hypothesis is that antibiotic B in this case is a better treatment for ulcers than antibiotic A. You get your groups set up, your control group, your test groups, maybe even a placebo, and you perform the experiment. You find that your placebo group, which in this case they have as a control group, they receive, either a true placebo or they receive one of the antibiotics that's been around for a while. And then this one has it set up where you're testing group A and B at the same time. So you have two test groups, collect your data, and data can be displayed right here in this chart, which lets you know which one seemed to be more effective. We'll see that test group 2, right here, they received antibiotic B and their results were superior to those who were given antibiotic A. And of course, the placebo shouldn't show much of anything. Okay. All right, if you have questions about any of this, please email me, let's talk, and I will see you soon with another lecture.